Hello class, welcome once again to our lecture. So this is the last part of our discussion for today. Okay, so this time we are going to discuss a related concept. We call it Gauss law. Okay, so to continue with our discussion on the electric field and electric forces. So here's the related principle. We call it Gauss law. So from the expression E electric field equal to KQ over R squared. So this can also be expressed as Q over 4 pi epsilon R squared, right? So from here, we know that the ratio, ratio of, the 4 pi R squared, 4 pi R squared refers to the area, because this is a spherical. Apologies, no? A while ago I had difficulty of relating this four because in our conversion I was looking for where is the four. So since this is spherical, so the the area of a spherical object is 4 pi. The surface area, no, sorry, the surface area of a spherical object is equal to 4 pi r squared. Okay, so that's why the expression becomes E equal to Q divided by area times epsilon. Now, if you are going to cross multiply, this is denominator plus the product of the area and the epsilon is the denominator. So if you're going to cross multiply A to the left, so we have here the expression of the product of the electric field and the surface area of the sphere. So equal to Q over epsilon sub 0. So this product class of the electric field and the surface area of the sphere is what we call the electric flux. So electric flux has the symbol, this one, P sub E. Okay, so this is the product of electric field and the spherical surface area. Alright, so these are what we call electric field lines, and this is what we call, this blue color here, spherical Gaussian surface. Okay, this is our illustration. So remember, we are now in the related topic called Gauss law. Now the spherical, the electric flux phi sub E is equal to the summation of the electric field multiplied by the cosine of phi, okay, multiplied by delta E. Right, so we have here an illustration from this general surface area. When we take part of it here, a small portion of it, so we have the angle, okay, the angle, okay, and then we have the electric field. This is normal to this surface area, and we have here the differential area. Okay, so we have here a relationship that gives us this. So P sub E is equal to the summation of a small portion of this, so that you can get all the total. And we have Q here, the charge distribution, and this is our Gaussian surface, a general um, presentation of the surface area. So this is called Gaussian surface. So Gauss law, so the electric flux. So we have the term here, electric flux, and you know what is electric flux, right? So this is just the product of the electric field and the surface area. Okay, so the electric flux through a Gaussian surface is equal to the net charge, net charge that is enclosed in that surface area divided by the permittivity of free space. Okay, so electric flux. So you know that electric flux is equal to the product of electric field multiplied by the surface area, Gaussian surface area. Okay, so electric flux through a Gaussian surface is equal to the net charge enclosed in that surface divided by the permittivity of free space, and it's given by this expression plus. And the unit, the SI units of electric flux is in terms of Newton meter squared per coulomb. Okay, so remember this SI units. So these are example 15. The electric field of a charged thin spherical shell. Um, the positive charge is spread uniformly over the shell. So find the magnitude of the electric field. Okay, so we are asked to find the magnitude of the electric field at A, outside the shell, and B is inside the shell. So we have two scenarios here. Okay, so from the formula, summation electric flux is equal to the summation of E cosine of phi multiplied by delta A. So differential area equal to Q, the charge divided by the epsilon. So we have here the illustration. So we have here the Gaussian surface area S1, and we have here the Gaussian surface S. Okay, so we have here the radius from the center towards this is R, and our small r is the bigger radius. Okay, so the solution. So we have the electric flux of A sub A equal to the summation, which is in this case we have summation of A cosine of 0, okay, multiplied by delta A. So A is a constant, so you can put it outside, and then you just sum up the delta area, sum up all the small areas, and this is equivalent to E, electric field, multiplied by 4 pi r squared. Okay, and this turns into something like this. So because electric flux is equal to Q over epsilon sub 0, and this one is also equal to this one, okay, this expression. So therefore we have now E multiplied by 4 pi r squared, this is the surface area of the sphere, equal to Q over epsilon sub 0. Okay, so from this expression, so outside shell of the Gaussian surface encloses all the charge. Now outside shell, so this outside shell, so encloses all the charges. So therefore we have E equal to small q equal to 4 pi r squared times epsilon sub 0. So inside the shell, here, so the Gaussian surface encloses no charge. Okay, so there's no charge here, so that's why it's equal to 0. Okay, so we have here the concept Gauss law. We have here electric field is perpendicular to these parallel plates, so perpendicular. Okay, so this is our spherical Gaussian surface. So this is our electric field. Now we have copiers and computer printers. So what is the application of this print concept? So this is applied in the printing machines. So we have here the copy output. This is the original document, and we have here the lamps down here. Then we have the selenium coated drum. Okay, this is cylindrical drum. Okay, and this part here is what we call the heated pressure roller. This is the corotron for drum. Corotron for drum, and we have the Corotron for paper. So this is the copy paper. Okay, so here's the process class. Okay, this is the Corotron for drum. This one. This is the lens. Okay, so charging the drum. Charging the drum. So first, the drum is charged, and then imaging the document on drum. Okay, then negatively charged toner. Here's the negatively charged toner. Then fixing the toner to the drum. Okay, this one. And therefore, Corotron for paper, so transferring the toner to the paper. After that, we have the heated pressure roller to finish the copy. So melting the toner into paper. Okay, so here's the basic application of this concept on the electric flux. So copier and computer printers, so path of scanning. We have here the laser beam. So this is the xerographic drum used in printing machine. Okay, so here's the flow. We have here instruction from computer uh, directed to the charging control. Okay, so we have here the ink supply, and we have the pump. So we have here the nozzle of printer head, and we have here the electrode. This is the deflection plate, and we have here the gather. So the flow, no, the flow of the ink to travel. So from here we have the nozzle printing head. So this is an electrode. So this is what we call the deflection plate, and the paper is here. Okay, so this is the process class. Okay, so thank you. I hope it gives you some idea plus about the application of this concept into printing machines using the concept of Gauss law. Okay, so our discussion on the electric field and electric forces ends at this point. So next time we will discuss about magnetic field. Okay, so thank you for watching this video. See you in our next session. Bye.